Assalamu alaikum students. In the last lecture, we have started with the introduction to DC motors, its equivalent circuit, and the magnetization curve of DC machine. In this lecture, now we will start the first type of DC motor, which is called the separately excited DC motor. As we have already discussed in the previous lecture, this is the equivalent circuit of the static part of the DC motor, and this is the equivalent circuit of the rotating part of the DC motor. As you can see in this circuit, there are two number of sources. One voltage source is connected with the field winding and the other one voltage source is connected with the armature winding. The source which is connected to the field winding is Vf and the voltage source which is connected to the armature winding is Vt. Both voltage sources are separate. It means we can control the voltage across the field winding and armature winding separately. If the number of sources are 2, then the motor is said to be separately excited DC motor. A separately excited DC motor is a motor when the field winding has a separate voltage source and armature winding has a separate voltage source. As you can see in this circuit, there are separate voltage sources. One is connected with the field winding called Vf and the other one is connected with the armature winding called Vt or terminal voltage. At this side of the circuit, according to Ohm law, If will be equal to Vf over Rf, that is voltage divided by the total resistance. As we know, Rf is equal to Rf plus R adjustable. Putting the value of Rf in this equation, we get If is equal to Vf over Rf plus R adjustable. By using this formula, we can find the current across the field winding. Now, at this side of the circuit, that is at the armature side of the circuit, the voltage source here is terminal voltage Vt, and due to the terminal voltage Vt, current is IL called line current. In case of series circuit, the current remains same. So that's why IL will be equal to Ia, that is line current will be equal to armature current because the circuit is series circuit. In case of series circuit, the current remains same. That's why IL will be equal to Ia. By applying the KVL at the armature side of the circuit, Vt minus Ia Ra minus Ea is equal to 0. Taking the Ea, Ia, Ra to the right side of this equation, we get Vt is equal to Ea plus Ia Ra. That is Vt is equal to Ia Ra plus Ea. These two equations are important for the DC motors. With this, now we will discuss the DC shunt motor. The second type of the DC motor is the shunt DC motor. Shunt DC motor is very similar to the separately excited DC motor, but only thing is that it shares the same voltage. Here, as you can see in this figure, if the field winding is connected in parallel with the armature winding, then the motor is called the shunt DC motor. A shunt DC motor is a motor whose field circuit gets its power supply directly across the armature of the motor. That is, in case of shunt DC motor, both field winding and armature windings are connected in parallel, and here there is only one voltage source. As we know, in case of parallel circuit, the voltage remains same. That is, if the terminal voltage is equal to 100 volt, then the voltage across the field winding will be 100 volt as well, and the voltage across the armature winding will be 100 volt as well. As we know, in case of parallel, the voltage remain same. The DC shunt motor is the motor in which field winding is connected in parallel with the armature winding. As you can see in this circuit, field winding and armature winding are connected in parallel. This type motor is called the shunt DC motor. By applying the KCL at this node we get IL will be equal to IA plus IF. As you can see in this circuit, the current IL is divided in two parts. One current is flowing in the field winding, and the other part of the IL is flowing into the armature winding. Therefore, by applying the KCL, IL will be equal to IA plus IF. And the current across the field winding, IF will be equal to VT over RF or VF over RF. As we know, in case of parallel, VF will be equal to VT. Therefore, IF will be equal to VT over RF. And similarly, the voltage across the armature winding will be equal to EA plus IA into RA. That is, VT is equal to EA plus IA into RA. When the supply voltage to a motor is assumed constant, as you can see in this circuit, in case of shunt DC motor, the voltage will remain same across the field winding and the armature winding. If the voltage across the field winding is 100 volt, then the voltage across the armature winding will be 100 volt as well. When the supply voltage to a motor is assumed constant, then there is no practical difference in behavior between separately excited and shunt DC motors. If the voltage across the field winding and armature windings are same, then there will be no difference between the shunt DC motor and separately excited DC motors, unless otherwise specified. Whenever the behavior of shunt DC motor is described, the separately excited DC motor is included as well. We assume the voltage VT will be equal to the VF. Now we will discuss the terminal characteristic of a shunt DC motor. First of all, we will discuss what is the terminal characteristic of a shunt DC motor. The terminal characteristic of a shunt DC motor is the plot between the output parameters of the machine. In this case, our machine is shunt DC motor. That is, the terminal characteristic is the output plot between the output parameters of a shunt DC motors. As we know, DC motors converts electrical power into mechanical power. The formula of electrical power is the input P in is equal to V into I, and the formula of the output power, that is mechanical power, is P out is equal to tau induced into omega. As we know, DC motor converts electrical power into mechanical power. That is, DC motor converts Vt into IL into tau induced into omega. As the terminal characteristics of a shunt DC motor, as we know, the terminal characteristics of a shunt DC motor is plot between the output parameters. Here, in case of motor, as you can see here, the output in case of motor, the output is mechanical power. That is, P out is equal to tau induced into omega. There are two output parameters. One is the shaft torque induced and the other one is the speed, omega. Basically, we want to find the relationship between shaft torque induced and speed omega. Then we will plot the behavior of shaft torque induced and speed omega. Therefore, the terminal characteristics of shunt DC motor is the plot between the shaft torque, tau induced, and speed omega. As when we load the DC motor, as we have already discussed, when we load the DC motor, then the torque load will increase as compared to the torque induced. When we connect the load across the DC motor, the torque due to load is tau load, and the torque is generated in the DC machine is the tau induced. When we connect the load across the DC shunt motor, the torque load will be more as compared to the torque induced. Due to this, the speed of the DC motor will start to decrease. That is, omega will start to decrease when we connect the load across the DC shunt motor. Now the question is, what happens to the speed decrease? That is, what happens when the speed will decrease? As we know, EA is equal to K phi into omega. When the speed will decrease, then the internal generated voltage will decrease as well. In case of motor, this internal generated voltage is called the back EMF. The relationship between the internal generated voltage and speed is directly proportional. When we load the DC motor, then the speed of the DC motor decreases. When the speed will decrease, then the internal generated voltage, or in case of motor, back EMF will decrease as well. As we know, in case of shunt DC motor, VT, that is terminal voltage, is equal to EA plus IA into RA. The value of IA will be equal to VT minus EA over RA. When the speed will decrease, then the internal generated voltage will decrease as well. When the internal generated voltage will decrease, then the current IA will increase as well, because the relationship between EA and IA is inversely proportional due to this minus sign. When the internal generated voltage or back EMF will decrease in shunt DC motor, then the armature current will increase. And as we know, tau induced is equal to K phi into IA. The relationship between torque induced and IA is directly proportional. When the current IA will increase, then the torque induced will increase as well. It means when we connect the load, due to this, IA will increase. When the IA will increase, then the torque induced in the DC shunt motor will increase as well. This will continue till tau load will be equal to the tau induced. The current IA will increase at that continuous till when the tau load will be equal to the tau induced at the low speed. Now, after little time, motor will again run at constant speed but at low speed. When we connect the load, then the IA will increase. When the IA will increase, due to this, torque induced will increase, and this will continue until tau load will be equal to the tau induced. When both the torque will be equal, then again the speed of the DC shunt motor will be constant but at low speed. As we know, the curve between omega and tau is like this. That is, at the start, the speed at no load, the speed will be maximum. When we connect the load, then the torque induced, when we connect the load, then the current IA will increase. When the current IA will increase, then the torque induced will increase as well. As we know, tau induced is equal to K phi into IA. When we connect the load, then the IA will increase. Due to this, tau induced will increase as well. But the speed will decrease. At no load, the speed will be maximum. When the load will increase, then the speed will decrease as well. But now the question is, how fast will the speed will decrease? It can be like this, or it can be like this. This is to understand this, we need proper equation. That is to understand how fast the speed will decrease. To understand this factor, we need a proper equation. By using this equation, we can find the relationship between the omega and tau induced. Now, we will derive the proper equation of tau induced and omega to find out the behavior of between the tau and omega. That is how fast the speed will decrease. As we know, in case of a shunt DC motor, the terminal voltage Vt is equal to Ea plus Ia Ra, as we have already discussed. And also we know Ea is equal to K phi into omega. Putting the value of Ea in this equation, that is in equation number 1, we get Vt is equal to K phi omega plus Ia into Ra. Now, we also know tau induced is equal to K phi into Ia. And here the value of Ia is equal to tau induced divided by K phi. Putting the value of Ia in equation number 2, we get Vt is equal to K phi into omega plus. Putting the value of Ia in place of Ia in this equation, that is in equation number 2, we get tau induced over K phi into Ra. Now we want to separate the value of omega. Therefore, we take the tau induced over K phi into Ra to the left hand side of this equation. We get K phi omega is equal to minus, here the sign is plus. When this factor we will take to the left hand side of this equation, this sign will be changed from plus to minus. Therefore, tau K phi omega will be equal to tau induced over K phi into Ra plus Vt. Now we want to separate the omega, that is we want to cancel out here K phi. To cancel the K phi, we will divide the K phi from both sides of the equation. Therefore, omega will be equal to minus tau induced over K phi square, because we divide both sides K phi. Here, as you can see in this equation, K phi already exists. When we divide the K phi in this equation further, then the power of K phi will be 2 into Ra plus Vt over K phi. Here, as you can see in this equation, K phi is multiplying with omega. To cancel out the K phi, we will divide both sides K into phi. The equation becomes omega is equal to minus tau induced over K phi square into Ra plus Vt over K phi. So this is our final equation. As you know, this equation is very similar to the y is equal to minus mx plus c. Here y is the omega, m is the tau induced over K phi square, m is the Ra over K phi square, and x is the tau induced. That is, x is the tau induced and c is the constant. Here the constant is Vt over K phi. Now, when the torque induced will be 0, as you can see in this equation, when the torque induced will be 0, then omega will be equal to Vt over K phi. Putting the value of tau induced 0 in this equation, we get this factor will be 0. The remaining factor will be equal to omega, that is omega will be equal to Vt over K phi. Therefore, the graph of omega will start from this factor. In this equation, Vt over K phi is basically tell us the initial point, and the factor R over K phi square is basically tell us how fast or how slow the speed will decrease when we increase the load. This factor is very important. This factor, that is Ra over K phi square, is basically tell us how fast, how slow the speed will decrease when we increase the load. This factor is basically the initial point of the speed, where the speed will start. As we know, in case of in the starting position, the value of tau induced is 0. In case of 0, putting the value of tau 0 in this equation, we get omega is equal to Vt over K phi. Let's suppose let the equation is y is equal to minus 2x plus 6. Let the constant is 6 and the value of m is 2. At the start, when we put the value of x is equal to 0, then the value of y will be, that is, here is the x and this is the y. At the start, when we put the value of x is 0, that is tau induced will 0, then the value of y will be 6. When we put the value of x is equal to 1 or tau induced is equal to 1, that is when we put the value of x is equal to 1, then the value of y will be equal to 4. When we put the value of x is equal to 2, then the y will be equal to 2. When we put the value of x is equal to 3, then the y will be equal to 0. That is, speed is decreasing more rapidly. Now, let this equation is equal to y is equal to minus x plus 6. Now, we reduce this factor, that is, we reduce the value of m, that is, we reduce the value of Ra over K phi square. In this case, now, if we put the value of x is equal to 0 here, now the value of y will be 6. When we put the value of x is equal to 1, then the value of y will be equal to 5. When we put the value of x is equal to 2, then the value of y will be 4. Now, by comparing these two equations, here the speed is decreasing slowly, here the speed is decreasing more rapidly. The factor is, we change the factor, we change the value of 2. Here we use the value of 2 and here we use the value of 1. It means this factor is very important. This factor is basically tell us how fast or how slow the speed will decrease when we increase the load. If we increase the value of Ra, then this factor will increase. It means then the value of this factor will increase as well. Due to this, the speed will more rapidly decrease. When we decrease the value of R, then this factor will decrease. When this factor will decrease, then the speed will slowly decrease. This factor is basically tell us how fast or how slow the speed will decrease. This factor is basically tell us the starting speed of the DC shunt motor. So this is the basic linear curve between tau induced and omega. This point is basically Vt over K phi. When the tau induced will be 0, then the omega will be equal to Vt over K phi. This point will be Vt over K phi. And this factor will tell us how fast or how slow the speed will decrease. Now, the question is, as the current Ia will increase, when we connect the load, then the armature current will increase. As we know, the tau induced is directly proportional to the armature current. When the armature current will increase, then the tau induced will increase as well. As we have already discussed, when the armature current will increase, then the armature reaction will be increased as well. When the armature reaction will increase, then the flux weakening problem will increase as well. If the flux weakening will increase, as we know, Ea is equal to K phi into omega. And here the omega, that is speed, will be equal to Ea over K phi. When the flux will decrease due to armature reaction, when the flux will decrease, then the speed of the DC shunt motor will increase as well. As you can see in this figure, when we increase the load, then the speed of the DC shunt motor is decreasing. If there is no armature reaction, then the plot will be linear. If there is a armature reaction, as we know, in case of armature reaction, flux start to decrease. When the flux will decrease, and the relationship between the flux and speed is inversely proportional. When the flux will decrease, then the speed omega will increase. Now, the plot between omega and tau induced will be like this. After some time, then the speed will start to increase as well with armature reaction. If there is no armature reaction, then there will be no problem of flux weakening, then the speed linearly decreasing. In case of armature reaction, flux start to decrease. As we know, the relationship between flux and omega is inversely proportional. When the flux will increase, then the speed will start to increase as well. This curve is with the armature reaction, and this curve is with no armature reaction. Note, if the motor has compensating windings, as we have already discussed, we can remove the armature reaction by using the compensating windings. If the motor has a compensating winding, of course there will be no flux weakening problems. If we use the interpoles and compensating winding in the DC shunt motor, then there will be no armature reaction. If there is no armature reaction, then there will be no flux weakening problem. If there is no flux weakening problem, then there will be no increase in speed. The speed will start to decrease continuously. That's it for this lecture.